It's been 2 years since I taught AP Chem. I hadn't gone back and looked to see what the order of the actual reading was when I was like, oh, this is the order I would teach it in, this is not how it goes. We'll just go in this order. Alright, so we've already reviewed some with chemical reactions and balancing our chemical equations. Most of this first part we talked about in first year chem, but some of us, it's been a while, so. Yeah, everyone has slept since then, whether you took this last year or 2 years ago. Alright, so we're starting on page 7. So, first type it talks about is synthesis. What was the big distinguishing characteristic of a synthesis reaction? Right, you should get how many products? 1. It doesn't matter how many reactants. You must get 1 product or it is not synthesis. Alright. Our next type, which is also pretty easily distinguished, is decomposition. What's the big distinguishing feature? Yeah. 1 reactant. It could be more than 2 products potentially, depending on what it decomposes into, but 1 reactant means it is decomposition. Those are usually pretty straightforward. These days, they do not expect you on the AP test to know this thing's going to do this kind of synthesis, this thing's going to do this kind of decomposition. They used to. One to watch out for is they do occasionally ask about, generally they tell you, carbonates tend to decompose to give you carbon dioxide and an oxide. That will show up, but they're generally fairly explicit about it. You used to have to memorize a lot more. Single replacement. So in their example, how do we classify zinc? Element or compound? Hydrochloric acid is a, zinc fluoride is a, and hydrogen is an element. So you should have element plus compound gives you element plus compound. So zinc being a metal replaced what? Hydrogen. Is hydrogen technically a metal? No, but for the sake of single replacements, metal will replace hydrogen, or metal will replace metal. The other thing to look for is this is where your activity series comes in, and we'll talk a lot more about our activity series in our next unit about electrochemistry, but okay, I'm trying to figure out how to write this. High on the activity series replaces low. So, for example, lithium is one of your most active metals. If you put lithium metal in with any other metal compound, it will replace that. Silver, on the other hand, really, really low. So if you put silver metal in most solutions, you're just going to keep silver metal. Your jewelry metals tend to be pretty unreactive. That's why we use them for jewelry, because they'll actually stay. Also why they got used for coins, because they would stay that metal. Silver will tarnish some, but not too badly. The other one to remember on activity series. So activity series for metals, you'll be given. Activity series for halogens is the other thing you have to look for. Halogen activity follows the table. Fluorine is our most active. Iodine is our least. So if I put liquid bromine in with hydrofluoric acid, is anything going to happen? No, because fluorine's already part of a compound, it wants to be part of the compound. But if I put liquid bromine in with hydroiodic acid, then the bromine will replace the iodine. Because bromine is more active, it wants to be part of the compound. If you're ever interested, there's actually an entire book about fluorine and the horrible, horrible things that went wrong when people were trying to work with fluorine at various points in history. There were a lot of them.
Stuff that's like in toothpaste?
Yeah, but that's fluoride, which is not going to be very reactive. It's already in a compound. It's happy. Trying to isolate and work with elemental fluorine, though, or hydrofluoric acid. Hydrofluoric acid is actually pretty reactive. The fun being a relative term, with hydrofluoric acid, so most acids just burn your skin. Hydrofluoric acid, like, seeps through your skin and starts interfering with, like, nerve function and starts eating at your bones and starts, like pulling calcium out of things. If you ever want to be really, truly horrified by hydrofluoric acid, there's an entire episode of ER. I haven't checked the how exact it is on research, but they're generally pretty good. There's an entire episode of ER in one of the early seasons where some guy gets a whole bunch of hydrofluoric acid spilled on him in an industrial accident. He spends, like, 6 hours just slowly dying, and there's nothing they can do because it keeps pulling all the calcium out of his bones and out of his blood, and you kind of need calcium for everything to function properly. And yeah.
Can you just take like calcium supplements until like eventually?
They couldn't. You can't get it in with the amount of hydrofluoric acid it got him. You can't put it in fast enough.
And there was no way to like wash it.
Because it was all in his.
Oh, it's like already.
It was in his system. Yeah, yeah. Hydrofluoric acid is terrifying. All right.
Where were they? What was the purpose?
Like he was in some plant that needed it for something, and there was something leaking, and he was a custodian or something, and decided to mess with it to see if he could stop it leaking, and made it worse. Yeah. The other moral of the story is, if something is leaking, you don't know what to do with it. Tell somebody else. Don't just poke at things.
Wasn't that a good idea on his part?
No, it wasn't. That's like both a brilliant and horrifying lab safety lesson in that episode. Alright, so double replacement. Double replacement we will talk a whole lot more about, but remember, double replacement is going to be our compound plus a compound, gives us a compound and a compound. They're going to switch partners. Please, please, please. What should you make sure gets partnered on your product side? What has to come together to make an ionic compound? A cation and an anion. Please, for the love of all that is holy, do not try and give me two cations together. Do not try and give me two anions together. Particularly watch out for NH4. It is positively charged. But we'll talk more about those because that starts getting into some more complicated reaction writing. And there's a couple sub-parts of that. Combustion. Combustion is always fun. So most of our combustion is going to be some plus what? What do you have to add for things to burn? O2 gives us...
Don't forget your...
Yeah, don't forget your O2's bad things happen. Your hydrocarbon can sometimes have oxygen, and that just complicates your balancing. It doesn't do anything bad. Be warned, they will sometimes talk about some of your synthesis reactions as combustion because you are burning. Like when you take magnesium metal and burn it, it's technically combustion. Are you going to get carbon dioxide and water out of it? No. So it's just a fancy synthesis. So watch out for that. And also remember, what is that reaction? Cellular respiration. The opposite way is photosynthesis. The biggest thing is you're going to get energy out of it. Combustion are always exothermic. So the biggest reason why cellular respiration doesn't actually make us burn is enzymes help it function at a more manageable level of energy release, and it's slower. All right, so now we get into our subsets of double replacement. Precipitation. What is a precipitate? Solid formed from two. Are they going to be pure liquids? They're going to be what? Solutions. So if you mix two solutions and you get a solid, that's a precipitation reaction. They like showing the newly... Okay, it's not even newly redesigned anymore. They redesigned it like most of 5 years ago, but I still think it was new. The AP redesign, they are slightly obsessed with particulate drawings. So in this case, when they're dissolved, they're all happy and floating around in solution. When they're precipitate, they'll draw them at the bottom. It is what it is. The particulate ones are usually not hard if you look very carefully at what you have. Which reminds me, I just remembered on this next test, I have to print one of the pages in color. We learned last time that like the particulate drawing is almost impossible to figure out if you can't see, like, because they're about the same size and they all end up gray and you can't tell what's going on. It's this one or one of the later ones, but yeah. The biggest thing on your particulate drawings, make sure things that are soluble are up in your solution. Make sure things that are supposed to precipitate are down at the bottom. Make sure you count, because sometimes they have you do stoichiometry with particulate drawings, and if you count, it's really easy. If you're just like, oh, there's a particulate drawing, this is just qualitative. No, sometimes it's quantitative. Count your stuff and do your really basic math. All right, so the solubility rules that this set wants you to know. We talked about some of them the other day. They're pretty basic. I don't know what's with the Big Mama, Big Daddy. It wasn't me. But, rule 1, nitrates have to be soluble. If it's a nitrate, it's soluble. It's a strong electrolyte. And we talked about this one. Group 1A and ammonium salts are always soluble. Halides. Where do we find our halides? The halogens, which is group. Right. Because what do you do when you change something into a negative ion? IDE. So halides are the negative ion version of the halogens. So if it's a halogen salt, it's going to be soluble unless it's got silver, mercury, or lead. There are some weird exceptions on that we don't get into in AP. They show up in other classes, though. Anything that's a strong acid, make sure you dissociate them. We talked about those the other day. Do memorize your list of strong acids. They're important. Strong bases are going to be your 1As always, mostly the lower half of your 2As. Do not write beryllium hydroxide or magnesium hydroxide is dissociated, unless it, for some reason, explicitly tells you they should be. But yeah, this one doesn't get asked about a lot. This one they will generally tell you other things. Nitrates being soluble, 1A and ammonium being soluble, halogens, except the exceptions, being soluble, and memorize your strong acids. Those are the big things. All right. So, knowing our solubility rules, predict what will happen. So I'm going to let you guys talk about these with your group for just a minute, and then we'll talk about them in this class. This is why I usually give you the one that doesn't give you the answers. But. And does everyone remember what AQ in parentheses means? Aqueous. It is in solution actively.
Or like is the
Alright. So, on A. Apparently knocked my VGA cable loose. Alright. on A, what would my two compounds be when we switch partners?
Barium nitrate and potassium chloride.
Is that the proper formula for barium nitrate?
Yes.
What charge does barium come with?
2. And nitrate.
So barium nitrate plus KCl. Would either of these precipitate?
No.
No. So this is actually no reaction. All right. Sodium sulfate plus lead nitrate. So what are we going to get?
Sodium nitrate and lead sulfate.
Are we going to get a precipitate?
Yes.
Yes.
Lead sulfate.
Okay, they didn't explicitly put it in there, but typically what it comes down to, if it's not something that's explicitly listed in that set of rules, it's insoluble. So sulfates in particular tend to be fairly insoluble. There are some exceptions that go other ways, but unless it's with a group 1 metal or ammonium, assume your sulfates are going to be insoluble until they tell you otherwise. All right, and then last but not least, we got KOH plus iron 3 nitrate. So we're going to get so what's my formula going to look like for that? And do I get a precipitate? Do I get a precipitate? Which one?
The nitrate.
The nitrate will be soluble. What about the hydroxide? No. But it's strong bases. If it's not group 1 or the lower half of group 2, it's not going to be soluble. Hydroxides are typically not. Alright. I touched on this very, very briefly last year. I'm planning on doing a little bit more in pre-AP this year. Complete ionic versus complete ionic versus net ionic. The nice thing is it will almost never make you write complete ionic because they're kind of a pain. Complete ionic are mostly there to help you write net ionic. And unfortunately, I don't have room to write half of this. So the first one, we've got aqueous potassium chloride is added to aqueous silver nitrate to form silver chloride precipitate plus aqueous potassium nitrate. So we start by writing our regular. So potassium chloride is KCl, and it tells us it's what? Aqueous plus silver nitrate, which would be, well, what's the formula? And aqueous, and it tells us that we have, stop unplugging. I keep knocking my VGA cable. Alright. So my first product is going to be silver chloride, which is AgCl, which it tells us is going to be solid, plus, which it tells us is going to be aqueous. Alright, now complete ionic, we literally just split everything apart that should be split apart. So, KCl, is this going to dissociate or not?
Yes.
So if it dissociates, we write K plus Cl minus. Plus, is AgNO3 going to dissociate? Yes, so we're just going to write it as its component ions. So Ag plus, how am I going to write nitrate?
NO3.
NO3 with what charge?
-1.
-1. Make sure you do not try to separate a polyatomic. I should have no N's. I should have no O's. I just figured out who this was. Ashley and... Alright. So yeah, make sure you keep your polyatomics as polyatomics. You split them, you lose lots of points. Alright, and then is AgCl going to be dissociated? No, because it's solid. Anything that's solid, anything that's liquid, anything that's gas, anything that's not aqueous has to stay together. Plus, is KNO3 going to dissociate? Yes. So K plus NO3 minus. And everything that's aqueous should be labeled as aqueous, and everything that's solid should be labeled as solid, but I just don't have space for things. So now, the fun part. And usually, like I said, you can skip this middle step. What looks exactly the same from the reactant side to the product side? K plus. What else looks the same? NO3? Anything else? No. So then our net ionic is where we only care about the things that actually do something. So our reactant side is now down to Ag plus aqueous plus Cl minus aqueous gives us Ag C, that's a C, not a parentheses, Cl solid. We don't care that it was potassium nitrate. Or we don't care that it was potassium chloride that we mixed it with. We don't care that we get potassium nitrate out of it. It doesn't do anything. All we care about is Ag ions are reacting with Cl ions, and we get the AgCl precipitate. Because it could have been sodium cyanide. It could have been, I can't think of something else. But yeah, it could have been all sorts of other things. Well, it could have been sodium chloride and silver nitrate's about the only silver that's soluble. But the K doesn't matter. The NO3 doesn't especially matter, other than it makes the silver soluble. If it's not doing anything, we leave it out in net ionic. So it's just a way to simplify. Alright, so let's do a bit of a challenge for ourselves. Let's, on this next one, try to just write the net ionic without writing everything and see how we do. So aqueous potassium hydroxide is mixed with aqueous iron 3 nitrate to form a precipitate of iron 3 hydroxide and aqueous potassium nitrate. So the easiest way if you're trying to skip to just your net ionic, start with what won't dissociate. What will not be dissociated in this reaction? Iron 3 hydroxide. So what did we have to start with? What of the reactant side will we care about if what we're trying to get out of it is iron hydroxide? Hydroxide and iron. So what charge will my iron have? Plus 3. Is this the end? Look at the reactants, look at the products. We have to balance the equation, so we need a 3 in front of the OH. They still have to balance for net ionic. So leave out the stuff you don't need, but it's still got to be balanced. We will not get into fancy balancing today, but one of the things we'll have to do, especially going into our next unit about electrochemistry, is balance redox reactions. They get a little tricky. They're not too bad. Alright, and then you can do stoichiometry with precipitation reactions. It's not so bad. Alright. So, let's skip to exercise 11, because it will make us do things twice. So, let's say these two groups, because before we get there, so exercise 11, when aqueous solutions of sodium sulfate and lead 2 nitrate are mixed, lead sulfate precipitates, calculate the mass of lead sulfate formed when 1.25 liters of 0.05 molar lead nitrate and 2 liters of 0.025 molar sodium sulfate are mixed. If it gives us stuff for both of our reactants, what kind of problem we're doing? Limiting reactant. So we're going to have to do stoichiometry twice. So these two front groups start with the lead nitrate. The back groups start with your sodium sulfate. What are we trying to get to? grams of lead sulfate. So, work with your group. What do we need before we can do stoichiometry? Balanced equation. So make sure you write your balanced equation first, and then we'll talk about things. So we've got Na2. That's weird. I don't know what it thinks I did. Well, but we're trying to do stoichiometry, so he's right.
Wait, so I am?
No, Oliver's right.
Oh. So we start with me. Okay.
Alright. So what do we need? What's the only thing we need to do to balance our equation?
Put 2 in front of something.
So it should not actually affect our stoichiometry. Alright, so yes, Oliver was correct. What do we never ever start with? Molarity. Because remember, what are technically our units on molarity? Moles per liter. And you don't start with the 2-unit thing if you can avoid it. So, we'll start with our lead nitrate, which has 1.25 liters of PbNO3, 2. And our molarity, where do we put the 0.05? On the top, because it's 0.05 moles in 1 liter, and this is still lead nitrate, which means on the bottom we need 1 mole lead nitrate. Lead sulfate.
Yeah.
Are we done at moles?
No.
We need to go to our mass. And so we'd have our 1 mole of lead sulfate. And anybody get our molar mass for lead sulfate?
303.266.
303.266 grams. Alright, and did we get our mass for lead sulfate for that? 18.95. Alright, and then for our other, we would set it up the same way. We would start with our 2 liters of Na2SO4, 1 liter, and our molarity, which is 0.025 moles. And again, it's 1 to 1, and our molar mass is the same. Alright, and so starting with our sodium sulfate, how much lead sulfate could we make? My back groups, did we come up with how many grams of... Okay. Alright, so, which one can we actually make? The 15. Anybody know why they reported it as 15.2? Why 1 decimal place? 3 significant figures. If you notice your volumes is 1.25 and 2.00. That's your lowest number.
Oh, that's probably going to be the AP test. Are they going to be stingy?
AP test is plus or minus 1 sig fig, so 15.16 would have been okay. 15.16 and the rest of things would have lost you the point. But so just when in doubt, find the number with the smallest. Don't try and be fancy about it, but find the number with the smallest and go by that. Plus or minus 1 sig fig, yep.
Wait.
So 15, in this case 15 would have also been an acceptable answer.
Okay, I have a quick question. So if the correct answer has one significant figure, could you have 0 significant figures?
No. If in a case like this, if you're trying to get one significant figure, you just put 20. Actually, which gets awkward. Usually it won't, but in that sort of case, the weirdest case is if you need like 2 or 3 significant figures for something like in the thousands. The safest thing to do, if you've got some weird numbers of significant figures relative to the length of your number, put it in scientific notation. Because anything in scientific notation that you bother to write in front of the time sign is significant. So let's say your answer is 1500, but you need 3 significant figures. If you don't write the decimal, it's got 2. If you write the decimal, it's got 4. So you'd write 1.50 times 10 to the third. You wouldn't normally do that to write a number, but it helps the sig figs be a little easier. Again, they give you plus or minus 1 sig fig, so don't get obsessed. Just keep an eye on it.
So you don't write 3 of them and they only want 1.
Right. Yeah, this is definitely a place where you don't want to give me everything your calculator gives me. Okay, yes.
So what I did was I started with molarity, but not for stoichiometry. I just did the algebra to find the grams, the moles. So and then you
started the moles and stoichiometry, which isn't wrong.
Okay.
I don't like doing it piecewise. Like if I can put it in one set of happy little tracks, I will put it in one set of happy little tracks. If that does not work for you, just make sure people can follow what you're doing. The AP test does not care as long as they can follow what you're doing. All right. This next one is basically like you do for titration. Neutralization, I don't know why they waited this long to talk about neutralization, but neutralization is another special type of double replacement. What do we always get when we do a neutralization reaction?
Water and a salt.
Water and a salt. So if we're doing a neutralization, it's water plus salt for our products. pH will not necessarily be 7. We will deal with figuring out when our pH is not 7 for a neutralization reaction the very first thing next semester. But just be aware, it's not always 7. Water and salt. It will not always be sodium chloride either. Remember, in chemistry, salt is any ionic compound. Be very aware of asking, well, okay, most chemists wouldn't do anything, but every once in a while chemists are like, oh, I have salt. Mm-hmm. All right. So, exercise 12. What volume of a 0.1 molar hydrochloric acid solution is needed to neutralize 25.0 milliliters of a 0.35 molar sodium hydroxide solution? Which of these do we want to start with? The milliliters. Because we've got 3 numbers, but only one of them has 1 unit. We can actually go ahead and leave it in milliliters if we're careful, because the only real change that needs to be made is if I've got milliliters here, we're also going to need milliliters. On the bottom, how many milliliters are in a liter? 1,000. So you can either do it this way or go ahead and convert to liters. Either is fine, just make it clear. And then how many moles are in my 1,000 milliliters? 0.35. Yeah, make sure we have things matched correctly because we're on NaOH right now. Alright, and when sodium hydroxide reacts with hydrochloric acid, what is my ratio? 1 to 1. And then, what am I trying to get to regarding my HCl? Liters, which means I need to use my molarity. Where's my 0.1 going to go? On the bottom. And then we'll just put 1 liter of HCl.
Put 1,000 milliliters.
Well, what's it want our answer in?
Liters.
Liters.
Oh, we already technically converted it. Oh.
Right.
Yeah.
So here, as long as these match, it's okay. You can then use liters over here. It's fine.
Okay. Wait, so will it usually say like what it wants?
It will usually tell you what units it wants. If it doesn't, just make sure you clearly label. Like, remember we ran into that, some of us may or may not remember, we ran into problems in pre-AP where, like, when we're using PV equals nRT, it would ask for a pressure but not tell you the unit. Because what is affected by pressure units in PV equals nRT? R. On an AP test, if they don't tell you what units they want, you have to make sure the units on your answer make sure the unit match the units for the math you did. Don't use 62.6 and then tell them that your pressure is in atmospheres, because you will be wrong. Don't use 8.314, I think it is, and tell them that it's in torr, because it's not. Make sure, here, it could be in milliliters, it could be in liters, but you better label it. Unlabeled tends to be wrong. Labeled incorrectly will be wrong. So if you did liters there and have the answer that's mathematically liters, but you label it as milliliters, there's going to be a problem. So just be careful with your labeling.
So like answers in scientific notation. So even if we wrote it just as a decimal, would they still count it, or would
So either would be fine. So you could write it 0.0875 liters, and it wouldn't be an issue. Because in this case, it's not going to affect your significant figures at all.
Okay.
They just like it for neatness. Alright. I won't do that one right now. Titrations. We've talked some about titrations. I think all of us managed to do a titration in first year chem. I'm honestly not sure. Tate, did Cubbage do a titration with y'all?
No.
I think so.
He was going to, and then he was like, yeah, we'll do it this day. And we were like, okay. And he was like, yeah, no, we'll do it this day. And we were like, okay. And then it like went by for 2 weeks, and he was like, yeah, we're not going to do it.
In his defense, the year before that, I didn't manage to do it either because I had just come back from maternity leave and life was insane. So, things to remember. Because designing titration reactions is really, really popular on the AP test. Your titrant is what's in the burette. So you want to pay attention to all your vocab. Your analyte is what's in the flask. Equivalence point is when H equals OH if it's acid-base. Watch out, redox titrations are a thing. We will do a redox titration next week. We may also do an acid-base titration next week. It depends on how much time we have for things. I want to do one, but it depends on time.
The analytes in the flask?
Analytes in the flask. Indicators. Indicator needs to be something that undergoes a color change. Phenolphthalein is common, but not the only thing. Do not tell me you're doing a redox reaction and using phenolphthalein as your indicator. You are wrong. Phenolphthalein pretty much only works for strong acid, strong base. They don't expect you to memorize what's good. They expect you to be able to figure out what would be good from a table, though. We'll talk about that a lot more when we get to acid-base equilibria in the spring. But when we do our redox titration next week, we're putting potassium permanganate into hydrogen peroxide. Does anyone remember anything important about potassium permanganate? Some of y'all may have looked at it in the Beer's Law stuff on Monday. It is violently purple.
I was gonna say it's really purple.
Like it's darker than most purple grape juice.
That's like really purple.
It's really, really purple. When you're doing a redox titration with potassium permanganate, you don't need to add an indicator because you're adding it until it's not purple, until it stays not purple. You want it to be very, very lightly purple when you're done, because you're putting purple into clear, and it should keep going clear until it stays light purple because you're done. Standardization is when you're trying to figure out a really, really good concentration. We are not going to exhaustively standardize anything in this class because it's not analytical chemistry. If you're going to major in something science-related in college, you will probably have to take analytical chemistry. Be prepared to standardize to 4 significant figures, plus or minus some ridiculously small number of standard deviations. It'll take a while. It's not my favorite. Important note, it's not scary, it's tedious, frankly. Important note on reading a burette. It is marked, funnily enough, that is totally a graduated cylinder they're reading and not a burette, because burettes are marked from 0 down. Oh, and my juniors have to go. Juniors have a ring presentation.
I didn't know.
I don't know if that early.
They're gonna hand you the stuff to
That
get
is
your
early.
class ring.
Yeah.
Okay, I don't want to go.
If you know you don't want a class ring, I will not report you to anybody if you don't go. But yeah.
None of them are going to
I got one, but I made
Priorities.
sure that
Yeah.
didn't miss it at school.
We're about wrapped up to where we're going to be today. So it's in the pack if you're going.
Okay, I'm not sure.
I frankly bought mine from Walmart because it was $100 instead of like $500.
I didn't get one.
I keep meaning to get my college ring, but by the time I was graduating college, they had stopped having the stainless steel ones because the stainless steel ones look perfectly fine and they're way cheaper. By the time I was graduating college, all you could get was white gold, and it was like $700, and I was not going to spend that on a ring. I thought it was a cool idea at the time. Like I said, I spent maybe $100 on mine, so
I want my college.
my parents were willing to pay it. That's.
You got yours at Walmart?
Yeah, Walmart has one, like you can order them online and do all the personalization and everything. Alright. They're going, they're just slower. Alright. But yeah, the big thing to remember when reading burettes, they are marked to the 10th, you're expected to be able to estimate to the 100th. Do not just give me the 10th and move on with your life. Try to go to the 100th. The AP test will typically give it to you with hundredths. That's where they're getting that. Alright. And then don't freak out when you see KHP. KHP is monoprotic, which means it has how many H's? 1. Other than that, just do stoichiometry. Yeah. If anyone's curious, KHP is potassium hydrogen phthalate. You will almost never see it written out because it's annoying.
I was thinking it looks like mechanics fighter.
It looks like
Yeah,
those little
because your top. So what it is it could be a diprotic acid, but if you have KHP, you've reacted it so that one of your H's is still there and the other's been replaced with potassium. Yeah.
It looks like a little robot claw.
Yep. And so all vertices are carbons. Any carbon that does not currently have 4 sticks, they're understood H's. I'm not going to draw the whole thing out, though, on potassium hydrogen phthalate, because it is just way too many C's and H's. Alright, so that's about where we needed to be today anyway. And so we're going to stop.